Hello, my name is Cyril Jacob Joseph. The date today is November 18th, 2023. Thank you for watching. So we are going to go over our gene mapping presentation, and this will be my presentation slide. And okay. So here we have a typical linkage problem with a given data set presented to us. On the left, we have a list of genotypes, and on the right, we have the progeny count for each. So first off, we want to identify the parental class. How do we do that? Well, the parental class would be the ones with the highest number of progeny counts. So in this case, we have plus, 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 and ABC as our parental cases. And then next, we want to identify the double crossovers. And those, in contrast, are the ones with the lowest number of progeny counts. So in this case, we have A++ and plus BC. And then all the ones in the middle would be single crossovers, and thus the recombinant class. So now we are going to compare our parents with both sets of double crossovers. We find out which gene is in the middle. And when comparing our parental with our double crossovers, we can see how A changes from the parental. And that same is different in the second double crossover. And this can be confirmed with this, finding the same trend with the second parental. So now we want to rewrite our parentals. With the A in the middle this time, we have BAC now and plus, plus, plus. Now, we want to determine which single crossovers are the ones paired up. And we do this by organizing this diagram here to the left. When organizing this diagram, we can start off with B, and here we cross over with A and go down. That makes up our first one in our crossover one. And then we go down to here, and we start off with B and cross over with A and go down. That makes up our second one in our crossover. And then in crossover 2, we can go down, and we can start with B and go down to A and cross over with C. That makes up our first one in our crossover 2. And then here we can go again, go down from B to A and cross over with C. So thus, since we have our single crossover events for each crossover, we can look back and compare to our original data table, which is on the right. First, we have to rearrange the genotypes for the single crossovers so that they have A as the gene in the middle. Now, when looking at this, we can identify which genes cross over with which by comparing it to our drawn diagram. Here we have B++ and AC, and next we have plus plus C and BA+. So now we know which genotypes and the respective progeny count occurred in which crossover. So next, in order to calculate the actual relative distance between each gene, we can use this formula which you add both crossovers and then add both double crossovers and take that sum and divide it by the total progeny count. So if we plug those numbers into our formula, we get 400 plus 420, which are the single crossover numbers we determined between B and A, and then we add the double crossovers together, which were the two lowest progeny counts in our table. And then I take that sum divided by the total progeny count, which was 5,742, and we get this decimal number. We then have to convert this number into centimorgans from Morgan, and we can do that by multiplying this number by 100. And there we get 18.46 centimorgans for the distance between B and A. And we can do that same calculation, same line of calculation between C and A, and we get 38.66 centimorgans as the distance between C and A. Next, we can actually plot this out onto an actual gene map. And we can start with the distance between B and A and C and A, and we just calculated it. And we can actually calculate that relative total length across these genes, which would amount to 57.12 centimorgans. Next, we want to calculate the coefficient of coincidence, which relates to the interference that may occur with chromosomal crossover arrangement during meiosis. Using this formula, we have the sum of both double crossovers, and then we divide that sum between the product of the distances between B and A and the distances between C and A, both of which is going to be in Morgans, along with the total progeny count. And when we do that, we get 0.3964. Next, we want to calculate interference, which is how extreme did one crossover affect other crossovers in the same particular chromosome region. And that formula is simply 1 minus the coefficient of coincidence we just calculated, bringing us to 0.6036. Thank you.